Good morning. Welcome on this webinar on noise prediction and mapping. My name is Erwin Hartog van Banda and I will be your presenter for this webinar. The agenda of today is on noise predictions, of course. Why would you like to do noise predictions? What are the methods available? What is the theory behind it? We'll go into the ISO 9613 method. How can you then build a computer model using software? And the steps of the noise mapping process. And at the end, there's time for questions. Why do you want to do noise predictions? Well, of course, you want to quantify the impact on the environment. You want to protect the environment and to compare it with legal or recommended values. Those are laid down in laws and legislation and guidelines. And then you want to predict the effect of measures. Where would you like to do your prediction? Well, on locations where people live, stay or work, but also in areas where a certain low noise level is expected or should be maintained. Nature areas, recreation areas, even cemeteries could be places, of course, where a low noise level is to be achieved and maintained. What do you want to predict? You want to predict the annoyance due to noise. And in many cases, that's the equivalent noise level at the facade, because the equivalent noise level is a good indicator for the annoyance due to noise. This equivalent noise level must, of course, be representative for a specific facade and for a longer period, for instance, 1 year. And this equivalent noise level must also be reproducible. I mean, it cannot be that one person calculates and the other person calculates and they have different results. So there must be a reproducible result. If you look at the representative and reproducible, for instance, for road traffic, if we calculate road traffic for over our noise maps, we base the calculation on an average traffic flow, on an average noise emission of cars, an average type of tires, an average speed of traffic, an average road surface, and also an average asphalt temperature. For instance, this last aspect, the average asphalt temperature, has an effect of 0.1 dB per degree Celsius. So if you would measure in a situation where it's 0 degrees Celsius and in a situation where it's 30 degrees Celsius, there would already be a 3 dB lower result in the 30 degrees Celsius situation. And that might also be the case why many tire manufacturers do their testing in warm countries to reduce the noise specifications of their tires, the tire road contact. If you look at the meteorological situation, again, it should be an average propagation. In many cases, many noise prediction methods assume a downwind propagation. But of course, we know it's not always downwind. You have, of course, the effect of wind direction, air temperature, humidity, air pressure. If there's snow, if there's water, reflections, etc. So also your meteorological situation should be defined in order to have a reproducible situation, because you cannot compare a calculation in downwind situation and a calculation in upwind situation. Looking at the noise prediction methods, basically you've got 3 types of methods. You've got empirical methods, theoretical methods, and numerical methods. Empirical methods are more based on measurements and practical findings, and those are the methods we are using today, like the ISO 9613, the NBPB 2008 for road traffic. The CNOSSOS EU is also maybe not as empirical as the others, but it could still be considered to be an empirical method. Then the theoretical methods, more based on physical principles, are, for instance, Harmonious and Nordic 2000. And then numerical methods, you could think of computational fluid dynamics, boundary elements, and parabolic equations. Theoretical methods are in fact, or can be, more accurate than empirical methods because they take into account more effects of how the environment really is. But the negative point of theoretical effect is that the calculation time is about roughly 100 times as longer as the empirical methods. Then if you go to numerical methods, they again are a step, they take more into account than the theoretical methods. However, those calculation times are again 100 times longer. So if you would do a noise map for the city of Amsterdam in a numerical method, most likely you will never end. I mean, it's not done in a lifetime. So that's why we are still using empirical methods. We accept the inaccuracy of empirical methods also because they are quick, they are fast, and you can do a complete noise map within a reasonable time. If you look at the theory, basically all prediction methods predict the noise, the sound pressure level, the LP, at a certain point, and they do that by starting with the sound power level, the LW, and subtract the attenuation between source and receiver, the A, the attenuation factors, like screening, geometrical spreading, air absorption, etc. So this is a kind of a basic formula for all noise prediction methods. If you look at the setup, so you start at the source, the sound power level, then between source and receiver, there are two steps done when you look at how the calculation actually is performed. First, the sources go into the pathfinder. And the pathfinder searches through the objects between source and receiver and also looks at the terrain model, the height differences. And when there are line sources, the pathfinder also segmentates the lines into points because most noise prediction methods have formulas based on a point-to-point calculation. So your line sources are split up into many points. In fact, many segments, and every segment is then considered to be a point, a source point. Then every source point is offered to the point-to-point propagation method. And for instance, the ISO 9613 only describes a point-to-point algorithm. It does not define a pathfinder, and also it does not define a source model on how to calculate the sound power level of a source. Because coming back at the source models, you've got industrial sources, road traffic sources, real traffic sources. For road traffic sources, many calculation methods like the CRTN, the NMPB, they have a source model included. That means that you only have to type in the number of the type of traffic, light vehicles, heavy vehicles, etc., the hourly flow, the speed, and the type of pavement. So, and those are enough parameters to calculate your sound power level due to a road. Okay, sorry. Coming back to the point-to-point, so every source point is calculated. The propagation is calculated, so the difference between the sound power level and the sound pressure level is calculated, inclusive meteorological effects. That's done in this point-to-point calculator. And then all propagation paths are accumulated, so it is summed up in order to get the total noise level at a receiver. So this is in fact the procedure for all noise calculations. So those steps are done in the software in order to get the total noise level at the receiver. And just like I said, in many cases, noise prediction methods only describe the point-to-point and a source model in some cases. The ISO 9613 does not describe a source model because the ISO 9613 starts with a sound power level. You have to find the sound power level. Okay, coming back or looking at the ISO 9613 method. It calculates the downwind sound pressure level based on the sound power level minus the attenuation. And this downwind sound pressure level, that's a equivalent continuous download sound pressure level. And it's a kind of an average downwind sound pressure level because you can have a exact downwind, you can have a little bit downwind. This is a kind of an average downwind situation. However, it does not handle, for instance, temperature, a real temperature inversion, a full temperature inversion. So that's not included in this downwind sound pressure level in the ISO. Then if you look at the attenuation, the difference between your sound power and your sound pressure, that's built up by the geometrical diversion, attenuation, air absorption, ground absorption, the barrier effect, and some miscellaneous effects. And then on top of that, the ISO 9613 calculates the first reflection. And it's in this formula, it says that the attenuation includes a correction for reflections, but in fact, that's not true because the A is calculated for the direct path and the same A is calculated for the reflected path, but then the sound power level is reduced due to the reflection factor of the facade in which the reflection occurs. Okay, looking at the wind influence. If you have a downwind coming from here to the receiver, we all know that the sound rays bend towards the earth. This means you have a good propagation. If you would measure in an upwind situation, then the rays bend up from the earth, and you could end up measuring in the shadow region, where the earth itself acts like a barrier. This part cannot be calculated by empirical methods. So you need a theoretical method like the harmonics in order to calculate in this shadow region. So be aware of this. That also means that if you want to compare your measurements with your calculations, you always have to measure in a downwind situation, because that's where the noise prediction standards, or most noise prediction standards, are valid for. And are, yeah. Then the ISO 9613 offers an option to convert your downwind sound pressure level to a long-term average sound pressure level. And the ISO does that by subtracting a meteorological correction. And this meteorological correction is a very easy formula. It depends on a local meteorological condition. And for the rest, it depends on the source height, the receiver height, and the distance between source and receiver. In the graph here, you see the graph for a C0 of 5. That means the further away you are from the source, the maximum difference between a downwind situation and a 1-year average situation is 5 dB. And for instance, in the Netherlands, that's defined by law that you always have to use for industrial noise a C0 of 5. For road and rail traffic noise, you have to use a C0 of 3.5. So this is a way to convert your downwind sound pressure level to a long-term sound pressure level. Then, if you look at the meteorological effect in Predictor, there are several options. Let me just close this one. Yep. There are several ways to calculate this meteorological effect. You've got an option for no meteorological correction. That means that the results that you calculate in Predictor will be downwind. And in many cases, that's the result that you need, because there are not so many countries like the Netherlands that prescribe a Z0 of 5. In many countries, they simply take, well, not simply, I think it's a realistic approach. They simply take the downwind situation, and you could consider that as a kind of worst case situation. However, like I said, it does not handle a real temperature inversion that can occur during the night. So this is one situation in Predictor, no meteorological correction. The other option is a single value for a C0 0.5, like it is in the Netherlands, for instance. There's an option for C0 per period. It's not used that much, I guess. And there's an option for concave per period, and that's an interesting one. There you can choose a stability class, a dominant wind direction, dominant wind speed. And in this case, the concave includes a temperature inversion situation. And so that's an option to calculate downwind with ISO 9613, and then also include a temperature inversion situation as a meteorological correction. And that means that it could end up about 2 dB higher, let's say, maximum. Then you have a C0 based on wind statistics. That's a German method. That's also an interesting method. And this is a method that assumes that if you have downwind, meet wind, you have no difference between your calculated result and your long-term average. So if you have a whole year downwind, then of course it's the same. Then side wind, there's a 1.5 dB difference with the downwind situation, and upwind, there's a 10 dB difference between downwind with a downwind situation. So this is interesting because then you can use wind statistics. If you know the wind statistics over a year for the day, the evening, and the night period in 30-degree angle steps, then you can calculate your average yearly average meteorological factor. That's an interesting one. So those are the methods you can choose in Predictor to calculate your meteorological correction. Then if you look again at the attenuation, you've got the geometrical spreading, atmospheric, ground absorption, barrier effect, etc. If you look at the geometrical diversion, that's the formula, an easy formula, 10 times the 10 logarithms of 4πd squared. And this is the formula which you might recognize as being the surface of a sphere. So it's a globe, the surface of a sphere around your point source. And the further you are, the larger the surface is. But of course, the further away you are from the source, also the sound intensity on every part of the surface becomes lower. And that's fully, depending on the surface of the sphere itself. This formula already at for instance 100 meter already gives you a 50 dB difference. So this is in fact the attenuation that gives you the highest attenuation. Then atmospheric absorption, through the air. You see that lower frequencies have low absorption, higher frequencies have higher absorption. This also means that the further away you are from the source, the less high frequencies you hear. And that's what we also hear. When we go away from sources, you only hear the lower frequencies. And in many cases, those lower frequencies are the most problematic frequencies to reduce, because higher frequencies can be, in many cases, reduced by absorption, adding absorption, but lower frequencies is a problem, because also, as you will see, barrier effects are less for lower frequencies and more for higher frequencies. So higher frequencies are in many cases easier to get rid of. Ground attenuation, this is a system where it assumes a reflection in the source, in the middle, and in the receiver region. That's why in the ISO 9613 you can define a ground factor for the source, for the middle, and for the receiver region. And here are the formulas in the ISO 9613 method. You see that for 63 Hz for the source region and the receiver region, it's always minus 1.5, and you add them up, so you always have a -3 attenuation, ground attenuation for the 63 Hz. And then the other factors for the octaves are depending on the ground factor. And for instance, if it's a reflective ground between source and receiver, then the G would be 0, and the ground absorption factor of 0. That means that everything here would be -1.5. This also would be -1.5. So that means if you have a source and a receiver region, the total sum will be -3 for all octaves. So for a full reflective surface, you have a 3 dB higher noise level at your receiver because it's a -3 attenuation, and this attenuation is subtracted from your sound power level. So it's -3 is +3. And here you see the formulas when it's not reflective. When it's, for instance, absorptive 1, then the high frequencies have a ground effect of 0. -1 is 0. But these, between 125 and 1000 Hertz, they are then depending on this factor, the A, B, C, D. And here are the formulas. And you see that the E powers, this is a full empirical formula, a best fitting curve through all kind of measurements that have been done in the past. If you look at an example of the ground effect, this horizontal bar gives you the effect per octave for a reflective ground. So that's 3 dB as an effect, as an increasing effect on the total result. But if you have a full porous ground, a ground factor of 1, you get a dip in the 250 Hertz octave band. And like I said, for the higher frequencies, you end up with 0. So if you make a mistake, if instead of making it reflective, you make it absorbing in your computer model, you make a mistake of over 20 decibels for the 250 Hertz octave band. So that's how sensitive these models are, of course. Yeah, well, anyway, if you make a mistake, you can expect that you have different results, but this is a very large difference. You have to realize that. The effect of a barrier. The ISO says a single barrier has an effect up to 20 dB. The single diffraction is a maximum of 20 decibels. Double diffraction can go up to 25. This is an example for single diffraction, and you've got here a source at 1.5 meter height, receiver 1.5 meter height, and then depending on the height of the screen, there are 3 graphs given. Height of 2.5, 3.5, 6 meters. What you see, they all have the similar effect, that there is less barrier attenuation for lower frequencies and more attenuation for higher frequencies. So barriers are better for higher frequencies than they are for lower frequencies. And it makes sense because for lower frequencies, the wavelength is bigger. So you could assume or think that the wave might pass over a barrier much easier if you have such a large wavelength. Because for those lower frequencies, the wavelengths are meters. And that makes sense. Well, for the higher frequencies, of course, the wavelength is very small, and then the beam, the ray, really hits the barrier. And then you've got this diffraction effect. Okay, how to build a computer model. So this is an example, a picture of a road, of a highway with two lanes in that direction, 2 lanes in this direction. It's on an embankment, the highway. There is a part of a city here with houses, sheds in the garden, gardens, a road, etc. So first you have to input your road. This is an example of a road traffic noise. And here already you have to decide where to put your road lines. The methods like the NFBB 2008 or the Dutch road traffic noise method, they do not tell you much where to locate your road lines. So you have to choose it yourself as a user. You can either choose one single line for the whole road, or one line per direction, or one line per lane. That's up to the user. One line per lane might not be that how do you call it, that does not make much sense if you do not have information on traffic per lane. So if you do not have traffic flows per lane, then it makes no sense to enter road lines per lane. Also, if you do not have traffic flows per direction, and you only need to know a kind of a total flow, then you even might not consider adding a lane per direction. However, assuming that you have information on traffic flow per direction, in this case, a line is input in one direction and for the other direction. Okay, the next is input of buildings. Here you put in the buildings And there's a decision to make. Do you also put in the sheds in the gardens? In many, in some countries, there's an additional guidance on top of the calculation method saying, well, sheds of 2 meters high and lower do not need to put in to your computer model. But again, it's up to you. Ground regions. So in this case, the surfaces that are reflective are being put in as a ground region. And in Predictor, you can decide what is the most dominant ground factor. If the most dominant ground factor is absorbing, like this is an absorbing area, the gardens are absorbing, then you can decide everything is absorbing except for the ground regions that are put in. And in this case, you put in reflective ground regions. Then height lines. So parallel to the road, you can enter height lines to create your embankment for the road. Those height lines in Predictor do not have to be ISO height lines, and height lines can go up and can go down. So if the road goes up, then also the parallel height lines can go up with the road and go down with the road. So that makes entering of those human-built embankments quite easy. Then calculation points, receiver points here, for instance. Again, this is up to you, because if your law in your country says you have to calculate the maximum noise level that can occur on the facade, then it might be of influence if you put your receiver point over here or a little bit closer to the edge of a building. And in this case, there might not be much difference, but in case of a barrier along the highway and that stops over here, then it might very well be relevant if you put your receiver a little bit closer to the edge. So be aware of that effect. Then in Predictor, it would look like this. And then if you take off the background map, it would look like this. Then, of course, you have to enter the properties of the road. And in this case, we've chosen the NFBB 2008 method. You can enter the properties for light vehicles and heavy vehicles, the flow and the speed for the day, the evening, and the night period. You can select the surface type, and you can select if it has a slope, if it has constant flow, etc. Those are options for the NFBB 2008 method. Then after your calculation, you can show your calculated values on the receiver. You can, of course, also calculate a grid of receivers and then show the noise contours, the interpolated noise contours in Predictor. But be aware that the accuracy of these lines are, of course, depending on your grid spacing that you have chosen. If you use a grid spacing of 100 by 100 meters, then the location of your contour lines are also accurate on 100 meter as a FISF rule. So be aware that the spacing between the grid points affect the accuracy of the location of your interpolated contour lines. Then the last part of my presentation, noise mapping. So doing a larger project. First, I start up with some examples. It's a noise map of The Hague with a total calculated area of the 98 square kilometers. Then a project in the UK. All projects are, of course, done by Predictor-LimA. An area of 388 square kilometers. Then we're going a little bit larger. The noise map of Thüringen in Germany. An area of 18,000 square kilometers. And then might be even the largest noise map up until now, an area of 130,000 square kilometers is the noise map of England. And this shows you all the tiles that were automatically generated during the process using the LimA software. And then at the end accumulated all the tiles again. So if you look at the noise mapping process, then the first step would be your data selection. In many cases, it will be a GIS data selection, meaning height lines, buildings, ground cover, locations of roads, railways, industry barriers, etc., bridges. That's a large part of your noise mapping project. Then the second part might even be larger in time and effort. You have to evaluate, to validate your data, and in many cases also economize. You have to check if there's missing data. Is it wrong data? Is it out of date? I mean, it could be that your ground cover data is not the same time period as your building data or your height line. So there's a mismatch between the dates of the separate data sets. Or of course, it's too detailed. And then you have to economize. You have to simplify your data in order to get reasonable calculation times. But of course, when you are doing that, you have to prove that you stay within a certain limit of accuracy. You cannot deviate too much from a full data set, and there are methods to prove that you can economize, you can simplify, and still stay within a 1 dB accuracy of your calculated noise levels. Then, of course, you go up to the calculation, and you always have optimization settings, error margin. For instance, coming back to the noise of England, that's why it's tiled, because if you would calculate a result in the north of England, it doesn't make any sense to take into account a road fully in the south of England. So that's also why they are tiled. But also within a tile, there's also a fetching radius. And again, if you're using those error margin and fetching radius, again, you have to prove that they are within a certain limit of accuracy. You cannot just simply optimize as much as you want. Then, if you have your results, if possible, you can compare them or should compare them with measurements. And in many cases, there should be beautiful would be to have long-term measurements available. Long-term measurements, because you also want to calculate a long-term equivalent result. So you need to compare with long-term measurements. But long-term measurements are in many cases not possible because of all kind of background noise that are not belonging to the sources. Then, step 5, you have to analyze your results and confront your calculated noise levels with demographic noise levels, with demographic data. For instance, you have to calculate the number of dwellings and people per 5 dB noise class. And that's a part of the European noise mapping project. And then, what's also part of the European noise mapping, you have to make a publication of the noise map, make it public to the public, and put it on the website. So that's in a short for time frame, the steps that you would need to go through in order to make a noise map.